Thank you very much. So I'm going to talk mainly about cars today. And just to recap for the few of you who weren't in Yoshi's talk, here's the context. A modern, unmodified vehicle. Oh, we're not getting sound. Why are we not getting sound? All right. Let me do this one more time with sound. All right. You're not going to see sound. So this is a demo that we did for DARPA in 60 Minutes with Leslie Stahl, where we remotely turned off her brakes as she tried to drive this course. She is saying, "Ah!" or something akin to that. That's really scary. And so this was an off-the-shelf, unmodified sedan, and it is not unique to this car. All right? And so I am not going to tell you how to do that, although I'm sure there are many of you who would like to learn that, and that's why you came, and unfortunately I'm here to disappoint you. I'm going to talk about why we can do that. Why do these vulnerabilities exist in automobiles, and what are the challenges in addressing them? Why is this not as simple as, hey, hire better people, automotive industry, and then it'll all be better? And then I'll talk a little bit about what role does the research community play and the different roles that it's played in trying to deal with this problem and some of the trade-offs in how it does this. To get us all on the same page, though, I'm going to talk a little bit about the technology so that we'll understand, as we get into some of these points, the whys. And so the first thing I want to disabuse you of is that a car is a mechanical device. All right? A car is a big distributed system that has wheels connected to it. And that has been true for really about 15 years, but today is super true. So it is probably the most complex distributed system that you personally own. If you have bought a car in the last 5 or 10 years, there are going to be 20 or 40 different computers. The term of art is electronic control unit, or ECU. They range tremendously in capability, from 8051 style microcontrollers up to multi-gigahertz power PCs or other system-on-a-chip devices. There are dozens of different operating systems and runtimes working together. The software parts, those components that control those, can change completely from year to year, be supplied by a different vendor. They are all internally connected. Your car is a big Ethernet. That's the way to think about it. And as time has gone on, they are increasingly externally connected, sometimes through things that are very obvious, like you have OnStar or Sync or something that very clearly is a wireless connection, and sometimes things that you would never even think of as being a wireless connection, like that thing on your radio that tells you the call sign of the station you're listening to. Well, how the hell does it do that? It's because there's a digital signal that's modulated on the FM band that you thought was analog, that is analog but has some digital parts now too that we decode in software. All right, so let's take a look at what a typical automobile looks like. This is a high-level depiction of a car that we looked at that had really 2 buses. You can think of these as 2 Ethernets. A high-speed bus, where high-speed here is like a half megabit, all right? So we're not, we're talking high-speed 1970s era that has all the drivetrain components. A low-speed one, ballpark 100 kilobits, that's dealing with things like HVAC and airbag and so forth. And they do need to talk to one another. And one of the myths, I think, is that you can separate these things. And that happens usually through a number of components that act as bridges and proxies. In our case, there's the body controller. And then a couple units that I want to point out. One is, in our car, there's this telematics unit, which has become a pretty standard feature, but was really pioneered successfully by GM through its OnStar system. And that has to talk to everything. So it can do remote diagnostics and unlock your car and recovery after theft and so forth. And then there's this little thing on the bottom that says OBD2, and that is a port that is mandated in the United States by law that connects to everything. All right? That is the Ethernet jack for your car. And this, in turn, runs a slightly different set of protocols than we're used to, built around what's called the CAN bus that has its own physical layer, and then a variety of manufacturer-defined specializations. All right. So from this, I want to talk about the first security problems that Yoshi highlighted, and that is that the inside of your vehicle is not hardened against attack. That is, once you get inside this network, all bets are off. And so the OBD2 port, which is that little dongle over there on the right, you will find in your vehicle, if you look underneath the steering wheel on the driver's side dash, it will appear there. And if you plug into that, all of a sudden you have access to everything. And so back in 2010, we showed, hey, if you plug into the car that we got, which now that Wired has outed all of this, we will say is a 2009 Chevy Impala, that we could do anything. All right, that from there we could control the brakes, we could control the lights, we could control the engine, and so forth. And then a little bit later, 2014, Charlie and Chris showed exactly the same thing for a 2010 Toyota Prius and a Ford Escape. And the reason that's important is that it shows it generalizes. It's not that like the Impala is a piece of crap. It's that, hey, the way that these cars are designed architecturally is such that once you're on the inside, that you can achieve fairly arbitrary results. And the reason for that is multiplicitous. So first, we have a totally open network. The way that these components are built, in part because they're built by a lot of vendors and are designed to be loosely coupled, is one of these traditional software bus-style architectures, where everyone puts stuff out on the bus and then other people consume it. And in fact, built into the CAN protocol is this notion that you are basically sending to an address that does not necessarily refer to a particular component, but you have no source address. There are no source addresses in CAN. You're just announcing stuff. And so that's the way that this stuff is built. And because it is a big distributed system, there is a huge amount of innate coupling between ECUs. The notion that you could separate the mission-critical stuff from the non-mission-critical stuff turns out in practice to be wrong. Like your keyless entry system, why does it need to control the engine? Well, on the face of it, it seems like it doesn't, but you need to be able to unlock the doors. That's what keyless entry is for. And it turns out that after you're in a crash, the component that detects there's a crash has to be able to turn off the engine and then unlock the doors. So it means that there must be a path through the system for that function that gets all the way from the locks and the keyless entry all the way to the engine. And it's not that there's one or two weird one of those. There are hundreds of those. All right? So give up on the notion that we're going to separate these two things. Anyway, consequences, quite a bit of the communication that goes on are effectively RPCs between these units, where they say, hey, a little switch went on, you should turn the left blinker. And so you can just listen to that and record it, and that's going to work because that's built into the architecture. It also turns out we use exactly the same network for maintenance. So when you take your car into the shop, the very first thing the mechanic does is he plugs into that port and now can put the car in all kinds of unsafe states, like bleed all of the brake pressure so that I can get there inside the brake drum, which otherwise I couldn't do because it's under pressure. And same network. So I just pretend I'm a mechanic, and all of a sudden I can put your car into unsafe states. And then finally, this is what we use for update. Although the original purpose of the OBD2 was basically to get NO3 measurements for part of the Clean Air Act, it has now been multi-purposed into the way that you measure and update every component in the car. And that is how we do it. And so as a consequence, you can reflash any of these units once you have access to the network. Now, there's an obvious criticism, and boy, did we get it in spades, which is, so what? You got inside the car, you plugged into the network, and you can mess it up. Big whoop, which I am paraphrasing from many of the articles that were written at the time. And that is a fair criticism. I got in the car. I mean, I could quibble, but I don't have enough time. But the challenge is that, in fact, it's not just the insides, that you can get to the inside from the outside without ever having any physical access to the car. So in 2011, we demonstrated remote takeover without any physical access and at arbitrary distance over multiple different channels, although the most spectacular of which was via GM OnStar, their Generation 8 version. And again, a number of years later, Charlie Miller and Chris Valasek demonstrate the same thing in the Jeep Cherokee, in this case leveraging vulnerabilities in the Fiat Uconnect, showing that this is a general issue and not a specific issue to one manufacturer. And there are a ton of remote compromise vectors, all right? And I will briefly, very briefly highlight what some of these are. There's one that we call the indirect physical channel. These are things where someone does require physical access to the vehicle, but not the adversary. So for example, we built an exploit that worked by re-encoding songs that would be put on a CD. They will play fine on your laptop, but if you put it in the car, it'll take over the car due to a vulnerability in the CD player, and from there it would spread over and take over the rest. The mechanics tools that people plug in, we did work with aftermarket dongles where we showed that were used by a very popular insurance company for pay-as-you-go insurance that we could take over there. And then there are a bunch that we haven't explored, but I guarantee you there are vulnerabilities, like charging stations for electric vehicles, the two-way digital communication. And there's a ton of these kinds of things. Then there's what we call short-range wireless, and I think Yoshi mentioned we found vulnerabilities in Bluetooth. Many new cars come with Wi-Fi. Keyless entry actually can be a fairly complicated protocol. The Department of Transportation is very likely to standardize a thing called DSRC, which is a proximate communications network for advanced collision avoidance, so you can hear about the car 3 cars ahead of you that's putting on its brakes. There are a lot of these short-range digital channels. And then there are the long-range digital channels, of which the most interesting is cellular, which are used for telematic services. But there's also things like HD radio, digital radio, satellite radio. All of these are digital signals that are being demodulated in software in a device that is directly connected to this network that, as I said, is totally unprotected, and once you're in, it's game over. All right, so I'm going to talk really briefly about the cellular one. It was convenient that someone asked a question just to give you a flavor of this. And so we were looking at the Generation 8 OnStar, and it was built around a 3G modem, but access to the device is via voice, via the voice channel. And the reason is that the first feature that everyone wants out of their telematics unit is automated crash notification. And voice still has better coverage than 3D digital, and what you really care about when you crash is that you can tell someone that you crashed, not that you have the best bandwidth to tell them about that crash. And so the consequence is that everyone uses a software modem, which is ironic because the cellular channel is itself digital, and so we do 2 pairs of D to A conversions in doing this, and you only get 200 bits per second out of it. It's a disaster, but this is what is done, and it's real Captain Crunch side channel stuff. Like there's a tone that you send down this analog line, and then you switch into digital mode. But there are 2 issues. So it turns out that the software modem, which is made by a little company named Airbiquity, which we did not find any flaws in, and the telematics code, which was written by LG, had different assumptions about how long a packet could be, because Airbiquity is a general piece of software that's supposed to be used by lots of different people, and LG wrote a piece of software for talking to the OnStar network. And why would anyone ever send a bigger packet than the OnStar network would send? And then there's a detailed error in the authentication challenge, but the end result is that we could encode a song, and this is another picture of Carl, who just takes the song, calls the car's phone number, and plays the song, and then the car gets taken over. All right, we called it the Song of Death. And so this is another demonstration. Again, for some reason, my audio, I think it's my fault. The audio isn't there, but this is where we're going to remotely turn on Alexi's brakes. And you can at least see him skid. There's a big, and he goes, whoa, or something like that. My sound effects don't do this justice. But it was bad. It was bad. And, even as, he knew exactly what was going to happen, and he reported, it was a little scary. So why is it so bad on the remote side? And this is actually, I think, a fair amount more interesting. No adversaries. So, in fact, from a Darwinian standpoint, how do you justify the investment for putting in security when no one is actually doing anything? You have a huge amount of pressure on feature creation. And one of the most important parts is that the OEM is not the developer. So Ford, GM, whatever, they are not writing all the software. They are the integrator. And this brings us to the supply chain issues. So the obvious part is, hey, the cost structure here is incredible. 2 pennies on a device will decide who ends up being the supplier. But it also means that because everyone wants to do reuse, everyone's supplier's code is one piece of code that they sell to everyone who has different needs. And so invariably, there's extra functionality in everyone's device that the manufacturer may or may not know about. Heterogeneity. All right, here's the one that I think is the most unintuitive. So if you walk into a car company and say, have you looked at the source code for your vehicle? I will tell you right now the answer is no, because they do not own it. All right, so all of these solutions that involve code inspection do not work because there is no party in the world that has all of the source code to a modern automobile. It belongs to the independent vendors for whom they have actually very tight intellectual property concerns about what they're going to share and for how much. And then finally, no one really has much experience with product security. OK. And I can talk more about these in the Q&A if people are interested. So now we discover all this stuff, and the question is, what do you do? What do you do? There's a big problem. It affects, in our case, about maybe 10 million vehicles. And we would like to make the world a better place. We don't wake up in the morning saying, you know what I really want to do is embarrass a bunch of people. I would like to actually make the world better. And so we can provide the information and the knowledge that we've acquired. And hopefully we can create some incentives to act on that knowledge, that we're not just throwing a paper over the fence that everyone ignores. But we would like to do so in a way that minimizes harm. And in our case, this was harm of the variety where all of a sudden, people start crashing into things. And this is a tricky balance. And so I'm going to talk in particular about some of our thought processes around disclosure in this domain, and some contrast with Chris and Charlie. All right, so here's the story. We had everything in early 2010, pretty much. All right, we delayed publishing the remote vulnerabilities in part because we were not completely sure about what to do about them. And so we made a number of active choices in what we were going to do, and one of them was to work directly with the OEM and with the regulator up front. That we were not going to do name and shame. This is the first time, I think, in public that we have talked about this, and this is only because Wired basically got them to admit it. And we did not release any code or details. You cannot read any of our papers and replicate our work, which is a very strange thing for scientists to admit. And there were a number of reasons for it. So number one, our primary goal was to have our work improve automotive security and hence make people feel safer on the road. We did not believe that there was anything unique either to the make or model or the OEM to the problems that we were finding. We just could not afford to buy 8 different cars and hack them all. Though we did get one review that was like, well, this would be more impressive if you had done it to 3 different cars. Like, geez. And the other part was that we realized at the time, both at the federal level and at the manufacturing level, there was very little capacity to do anything about the problem at the time. They were, I think, completely shocked with what we showed up with. And the notion, there was no incident response team. There was no, here's how you fix 10 million cars. The regulators had no idea what even to do. They didn't have anyone who understood anything about cybersecurity. I mean, it was really a disaster. And so if we put all of that out there, there were going to be a whole bunch of people who had the means to make many millions of cars be able to crash on demand, and it was not clear that they were going to be able to fix anything anytime soon, which makes it hard to sleep at night. So what happened? I'll talk about the plus parts first. In the short term, we worked pretty closely with GM to fix all the things we found in the next model year and in the Generation 9 OnStar, so the particular bugs we found got rid of. And there were a bunch of mitigations that got rolled out in the cell carrier that were not foolproof, but made it harder to do some of the things we did. In the medium term, GM really got security religion in a big way. They have a CISO just for product security, so not the IT side of the shop, but like making cars secure. They have 100 people. That's just their job to make sure that GM's cars have cybersecurity in them. There are a whole bunch of changes to both development practice and what they do, quite a few adopted from other people's security design lifecycle kinds of processes. They got a bunch of training. They changed their contracting practice in terms of what they have their suppliers do. And the design input has gone into the next generation of electrical design. So I'm not going to tell you that there are not vulnerabilities in GM's current cars, because I don't know that there are, but come on. They're big and complicated. But they're in a much better position than they were when we started in 2010. But that didn't do anything for all the Generation 8 vehicles out there, which, again, probably in the 10 million range. This is a tricky decision, all right? We could have made a big stink and forced a recall. And you got to think about what's the cost benefit on that for multiple reasons. One is there's actual costs, and ballpark, $200 per vehicle recall is cost to manufacture. But the other is that it's very rare that you actually get even the majority of vehicles fixed in a recall. People just don't bring them in. And so you're going to have a whole bunch of things on there on the road for a long time. And so then you say, what is the rediscovery risk that someone else would have come up with this? And so we made a decision not to do anything. 5 years later, and this is a pretty interesting Wired story, it comes out that GM remotely fixed all of Generation 8 OnStar units. The reason this is interesting is Generation 8 OnStar has no ability to do a remote update. All right? So I'm going to let you use your mind to figure out what must have happened. I am not saying that GM hacked millions of its own cars. But something happened. And it's incredibly ballsy. All right? So by contrast, Charlie and Chris did everything very public. 2013, their OBD2 stuff, they disclosed completely publicly. These are architectural issues, so there's no fix. I don't think this was a big deal one way or the other. UConnect is much more interesting. There, they did coordinated disclosures. So they talked to Fiat and NHTSA well in advance. The patches were available before their public release of details or code. Fiat instituted a voluntary recall under incredible pressure from NHTSA, which is the National Highway and Traffic Safety Administration. And conveniently enough, there was a mitigation at the cell level that pretty much blocked the pure cell-oriented compromise. So there was a real protection at the network level. Unprecedented impact on public perception because they were on Good Morning America and so forth. All right, I'm going to skip this part because I'm at the end, some musing about which one of us was right, and we can do that in Q&A. There's some pretty interesting, I think, trade-offs there. I will talk for 30 seconds about indirect things that have happened. One, every manufacturer on the planet either has remote update and admits it, or doesn't admit it, or is about to announce it. Remote update is now a standard thing in cars. So you should just, Windows update in all your cars. That's the way it's going to be. And it's because the cost of not having it is too great. The Society of Automotive Engineers, which is the standards body, now has cybersecurity standards as a direct result of all the research that's gone on here. NHTSA, in fact, has now a cybersecurity testing lab. And for better or worse, there are 2 currently drafted bills, one in the House and one in the Senate, and at least 2 more on the way focused on cybersecurity vehicles. And I'm happy to talk more about that in Q&A. So finally, to summarize, 2 things I want you to remember. Number 1, automobiles, computers with wheels, all right? It's not the other way around. That there are a lot of complicated issues that make it challenging to fix these bugs. It's not as easy as just saying, hey, let's add some encryption to that. But it is a place where the security community, I think, without any kind of ambiguity, played the key role in pushing this stuff forward. And then finally, disclosure is a pretty tricky question when you have real-life harms. And there are different advantages to doing it each way, depending on what your goals are. With that, I'll stop and take any questions.